Mm-hmm. Hello, everyone. Welcome to this practical session of the Copernicus Marine Service workshop dedicated to the Northwest Shelf Seas. My name is Andrea Carvalho. I'm a training officer at the Mercator Ocean International, and I'll be joined today by Ergan Fouché from Novelties. Hi, Ergan.
Hi, Andrea. Hi, everyone. Thank you all for being here today. I'm an ocean engineer from Novelties, and I'm very excited to present this session. Okay, so here is the platform that we are using for the workshop. In this platform, we will send you the link in the chat probably. In this platform, you can find all the material that has been developed for the workshop. You have the tutorial videos, you have the e-learning material, the replays from yesterday, and the records from today will also be available tomorrow probably. Yeah, so everything you need, everything's on the Padlet. We strongly encourage you to ask a question. You can talk in the chat, but for the questions, we would like you to use the Slido application. The link to the Slido will also be sent in the chat. And so after each session, we will have a Q&A time. So we will answer your questions. And if we don't have time to answer them during the session, they will be answered later, and you will have a file with all the answers.
Exactly.
So yeah,
so
that's
here you have
the QR
yes.
code to access the Slido.
Just give you some extra seconds so you can type this code.
Yeah, and the link is now in the chat. And so here's the program of today's session. We will have 1 hour of presentation of the Jupyter notebooks, then a presentation of the MyOcean viewer, and finally another hour of QGIS tutorials. If you're only interested in QGIS or MyOcean, you don't have to attend the whole sessions. We will try to be on time, and we will follow the agenda, so you can join whatever session you're interested in. So that's it for the program.
Exactly. So we could give the floor to Alexandre Romero.
Yes.
Also from Novelties, who's going to give us a little tutorial on Jupyter Notebook.
Yes, thank you very much, Andrea. So my name is Alexandre Romero, and yes, I'm very happy to be here and to present to you how to manipulate the CMEMS products with Python through Jupyter Notebooks. So I'm going first to present you a tutorial for beginners with Python and CMEMS products to show you how to retrieve data from CMEMS, and then how to do basic operation, displaying, plotting maps. So that's what we are going to do now. So sorry, I forgot to share my screen. Here we go. Is it working? I don't know if you're seeing my screen at the moment.
Yes, we see it.
All good.
Perfect. So this is the Jupyter Lab. If you want to follow or to play yourself with the notebooks, I advise you first to copy the training directories from the share notebooks training 2023 and copy the beginner notebook folder to your home directory in the Jupyter Lab. You can do it with a simple command in the terminal, such as this one, for example. So that way you will be able to execute the notebook yourself, as I'm doing as I'm doing it here on this presentation. Okay, so let's get started. So in this session, I will show you some products over the European Northwest Shelf. More importantly, the biogeochemistry analysis and forecast product. If you click on this, you will see a brief description of the product. So it contains many variables, but in this presentation, we will focus on dissolved oxygen in the ocean. So if you want more information, there is the user manual on this page, which will give you all the information you need about all the variables, units, and ways that the data is computed. And later on, we also look at some in situ measurements, which here are retrieved from a fixed mooring instrument in the Atlantic Ocean. When we get to this part, I will also show you how to retrieve this data because you'll have to go to a different CMEMS portal. So we'll see that in the dedicated section. Okay, so with the CMEMS portal, there are several ways to download data. Of course, you can do it from the CMEMS portal, from the website. But in Python, you have other ways to retrieve the data you need. There is a multi-client solution, which consists in a script to automate the downloading of the products that you require. So here is an example of the request that you can execute to get data. So here is a call to the multi-client library. Here the server where the data is stored. And then you will have to write all the different characteristics of the products that you are requesting. So here is the ID of the product. Northwest Shelf and this forecast. This is the ID of this product that you can see here. So here is another identifier of the product that you also need to write. And then you will have to enter the minimum, maximum longitude and latitudes, and the dates for which you want data. So here, for example, requested data from January 2021 to the end of the year 2021. So a whole year of data. I've specified that I want the oxygen variable. And here is the directory where I want my product to be downloaded. And here should be my user credentials, so username and password, which of course I'm not writing on this screen. So yes, here is the example of what is displayed once the request is executed. You can also download products with through the FTP server, which works in a similar manner. Same thing, you have to enter your credentials, username and password, specify the FTP address, and same as before, here are the two identifiers of our product. And the files will be downloaded and should be downloaded in the first in the directory where your notebook is located. Finally, CMEMS provides the OpenDAP solution to download data. So in this way, you have to download the script from CMEMS, which is opendapconfig.python. So which is for me located here beside my notebook. So when you execute it, you will have to enter same thing, your username and password. And well, I'll show you later on how to download a product with this solution. So now we have downloaded our products, and now we're going to manipulate them. We are going to use Python, of course, with a few selected libraries in this training. So if you're already familiar with Python, you're probably also familiar with the NumPy library, which is widely used to manipulate data arrays. We'll use X-arrays to open the data, which is very convenient for this format because CMEMS data is most of the time in a netcdf format, .nc, and X-array is very convenient to open such files. And Matplotlib and Cartopy will be used to plot the data, to plot graphs and maps. So I'm going to execute this cell to import all those libraries and load the files that I have downloaded. So here is the oxygen file, and here is the file from the in situ measurements. And in this cell, as I said, there is the same dataset, so with oxygen dataset, but open through the OpenDAP solution. So here is the link to the product through OpenDAP that you can copy paste from this menu here. You can retrieve it on the product page, data access, and then you'll have access to all the links you need. You'll select, in this case, this one, because it's the dataset that has the O2 variable that we are considering today. Let's now explore the files and see what's inside them. So we have opened the O2 dataset with X-array. So let's see what X-array dataset looks like. We have several variables in this file. So as we can see, it's a data with latitude and longitude coordinates. It also has a time coordinate. And clicking on these icons, you can have more information about the variables. So here gives, this icon enables you to display the attributes of the variable. So here it's about time, so it's pretty self-explanatory. And with this icon, you can see a sample of the values in the data. So for example, the first value here is of course 1st of January 2021. The second one is 2nd of January 2021. So it's daily data, and it goes until the end of December 2021. We see that we have a depth variable with 3 levels. So our depth apparently is in meters. So apparently we have data at 0 meters, so at the surface, at 3 meters deep, and at 10 meters deep. So we have to take that into account when analyzing the data. And we have a variable of interest, oxygen. So we can see that the mole concentration of dissolved oxygen in the water in millimole per cubic meters. And yeah, the dataset is too big to display values, but we will visualize them in the next sections. So first of all, let's see some basic manipulations of the dataset. So I've displayed some values using this icon, but if you want to consider only one variable in the dataset, you can call it between brackets, just like this. And here the time variable will be displayed. So now we have a full year of data, but what if we want to see only a few dates in this dataset? So if we want to see only one date and that we know the exact date in the dataset, we can select this date with the cell function. So here we've selected the 1st of November 2021. But you don't necessarily know all the exact dates that are in the dataset. And when this happens, you can always, choose the date of interest and look in the dataset for the nearest possible date that is available. And to do this, you just have to add the method nearest in the cell function. Apart from that, you can also, yes, select the data from the index. So here will be the 9th date in the dataset if we use this method. So here the function of selection is called iCell, I standing for index. So same thing, the 9th date here is the 10th of January, which makes sense. Okay, and this is the dataset that we have downloaded through the OpenDAP solution. And as we can see, it has the same format. The only thing is that through OpenDAP, we've downloaded directly from the link. So we didn't have any, did not select any dates when downloading the product, which is why here our product has data from 2019, from May 2019 to, well, to today, actually. And of course, to solve this and get only the data on the time frame we want. So here, the year 2021, you can select a date range in the data using the method slice here and providing your start date and your end date. So here we see that it worked 1st of January to 31st of December 2021. Okay, so we've done some subsetting of the datasets. Let's now visualize the data and see what it looks like on a map. So here is a reminder of the data structure of oxygen. And we are just going to draw a map of the oxygen concentration at a specific date. So this is the line where we do the selection. So we are selecting the variable O2, making sure we are considering this. Selecting, for example, here the 1st of June 2021. And this function here is a selection on the depth. So here we're selecting depth equal to 0. So we will only consider oxygen dissolved at the surface of the water. And the following lines are all related to the drawing of the map. So here is our first result. So yeah, you can see that there is less concentration near the coast, but more in open ocean. And yes, as a first exercise, you can play with the minimum and maximum values of the color bar to better visualize well, the oxygen concentration and the contrasts. I think I have time to quickly show you what it could look like. So let's, for example, narrow the minimum and maximum values. So here I've narrowed my range of dissolved oxygen concentration, and we can see that the map has a lot more contrast than before, which makes sense. So if you're executing this notebook yourself, you can play all you want with those values. And of course, yes, if you want to zoom in on a specific region, you can change the extent of the map. Let's do quickly an example here. I'm going to zoom on this tile, for example. So I can see that it's between 0 degree longitude and 2.5, and 50 and 52 degrees in latitude. So I'm just going to modify the extent of the map, which is defined here. It takes some time, but hopefully it's going to work. Yes, so it's a very, very strong zoom. So yeah, it's a little pixelated, but the important thing is that you learn how to zoom in on any area you like. Up. Okay, on to the next section. In this section, so we will, in this time, look at time series of data. And this is where our in situ measurements will be considered. So this is our dataset. I will just quickly show you how to download in situ measurements from the CMEMS portal. You'll have to go to this portal, so the Thematic Assembly Center website of CMEMS. The address is here. So it gives you access to plenty of different in situ stations all across the globe. In this menu, you will be able to select the area that you want to consider. And more importantly, the following will allow you to select the type of data that you want to see. Here we're considering oxygen. So let's see what are the in situ points that provide oxygen measurements. So we have example here. You can select them and then download the data if you are interested. So it's straightforward. It's not too complicated. And of course, you have many filters that are provided, from depth levels to dates. You can filter by a type of instrument. So there are plenty of things that you can select in this menu. Back to the notebook. So I've downloaded the data from one of those points. I will show you which one in the next cell. So when the data is downloaded, you can see that this time there are many variables because we were not able to select them before downloading them. And we are going to consider the OSAT variable, which here is called the fractional saturation of oxygen in seawater. So it's not exactly the same variable as in the geochemistry dataset, but it's still a measurement of oxygen, which is what we're looking for in this notebook. And of course, if you're interested in other variables, you can see practical salinity, temperature here. So there are plenty of stuff to play with this data. So this mooring has taken measurements during a long period of time. Let's see what they look like. So here I've plotted the location of my in situ point, which is here. And here is the time series of the measurements. So we can say this spans the period from around the middle of 2016 to nowadays. We can't see much here, but we can always do the subsetting that we have shown before, selecting a shorter time range to see better what the time series look like on the shorter period of time. I'm just checking the time to see if I can show you. Well, do the demonstration. Up. I'm just going to select a shorter date range to have a better view of the time series. So let's say I just want to have 6 months in 2021. Up. Just going to add this selection here. No, actually, no. Oh, okay. First time, first mistake. Oh, okay. So yeah, when you're dealing with different data sets, you have to pay close attention to the names of the variables. So here I've kept the time variable of the previous data set, which was written in lowercase, and here it's uppercase. So that's a detail that you have to pay attention to. And now we should be fine. Yep. So here are the oxygen measurements only between June 21 and December 2020 and December 2021. So we are closer and we can see better what the data looks like. Okay, let's do some more manipulations. So we are still with our oxygen dataset from the biogeochemistry analysis. And this time, what we're going to do is plot an oxygen concentration profile along a line in the ocean. So here is the example. So this is the surface oxygen concentration profile on the 1st of June along this line here, this red line across the channel. So to do this, I've just selected the maximum and minimum latitudes I want my line to go to. And I'm looking at a constant longitude, so because it's a vertical line. And still, I'm selecting only depths on the surface level. So I'm setting depth equal to 0 and selecting it here. I'm selecting the nearest latitude and longitudes to what I have defined here to make sure we have data to plot. And that is our result. And as an exercise, you can always change these latitude, longitude values to plot along a different line, perhaps an horizontal line from the coast of England to the Netherlands. It's just as you like. You can do this as an exercise. Alors, here is another section. So in this manipulation, I will show you how to calculate the variation of oxygen concentration between two dates. So here as an example, I'm just selecting oxygen concentration on the surface on the 1st of January and here on the 1st of June. So I'm just storing this in two different variables, January and June. And with the X-array format, it's very easy to just do a subtraction between the two sub datasets. So here I've displayed it. It looks like there are a lot of non-values, but once you plot it on a map, this is the result you get. And so as an exercise, I've shown you how to plot maps before. So you can use the same methods to plot this type of map of variation. We can see that between June and January, that the concentration of oxygen has mostly increased in open ocean, but a little bit decreased on the coasts. And finally, here is a little section to show you how to create an animation with X-array datasets. So what we're going to do here is retrieve the data of oxygen concentration at many different dates and plot the animation to see the evolution with time visually. So in this section, what I'm doing is first resampling the dataset to have not daily values but monthly values, which is why I'm specifying time 1M. And I want monthly average, so I'm calculating the mean over time. I will do an animation to see the evolution from January to June. So I'm selecting only the data from January to June 2021. So here's our new dataset. We can see that we have only 6 time values, 1 for each month. So this cell is the one that draws the 6 different plots and saves them. So it just takes some time to execute, but I have here, I am here saving the 6 different images in this folder. So I already have them, but as the execution goes, well, those will be loaded again. Okay, the cell has finished executing. So here I can execute this one, which will make the animation from all the images that I have produced. So to get a quick look, we can see that I have 1 image for each month and each one is different. So now we're going to plot that with the last cell and see what it looks like. It was very quick, so I'll just execute it once more because it's just stopped after June. All right, so I don't know how time we have left, but anyway, I'm thanking you for your attention on this notebook. And of course, as I said, you can copy it in your own workspace and play with it all you like. And well, from now on, guess I can take your questions if you have any.
Thank you, Alexandre. All right. We have certainly a few questions for you already. I will share my screen and share it with you all. There. And yes. So, first question from Natalia Stamataki. Hope I said that right. Which login password should we use to access Jupyter Hub? Oops.
Well, you have to use the same logins that you use to connect to the CMEMS portal. So this should work.
Exactly. You just have to register on Copernicus Marine Service and you will automatically have access to the Jupyter Hub. On the participant manual, you also have the link to access the Jupyter Hub and where you will find all the notebooks that we will present today, but also the ones that have been developed before. Second question, maybe we have time for the other question. Yeah, I think so. To use MOTU, is it mandatory to specify the lat and long in the arguments? It does not assume the boundaries of the data set specified.
I don't think you necessarily have to specify the latitude and longitude. I still recommend to do it because then you will end up with very large data sets, and you will have probably memory issues and download time issues if you don't specify an area of interest in your request.
Okay, and one last one. You said that the OpenDAP service is only possible to get full data set, but the threads server also has a subsetting service. Is this faster or slower than Mod 2? If you
It's a good question. I haven't really
I
timed
think
the
Martin
different
maybe,
solutions.
maybe Martin would be more comfortable answering this question.
Yeah, sure. Martin Pasquier is with us today.
Hello, everyone. It is indeed possible to subset through the OpenDAP service. And by experience, I would like to say that Motu might be slower than OpenDAP service. But I don't know really if it's really slower or not. It's just another service and access to download our data. Maybe you can tell us more about your question, Francis.
Yeah, do not hesitate to ask your question again more specifically, and we'll answer it, and we'll put the answer on the Padlet.
Thank you.
I think we have a little demonstration of the advanced notebook is right now.
Yes.
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 We can certainly take more questions afterwards. Don't hesitate to continue posting the questions. And yes. So stop sharing whenever you want, Alexandre.
Yes, I'm sharing my screen again. It should be working. Can you see it?
Yes, we can see it.
Perfect. So yes, as a little demonstration, I will now show you the second notebook, which is a case scenario over the Northwest European shelf with a little more advanced manipulations of the CMM's data. So I've chosen to look at one variable, which is net primary production, which, as a reminder, is the rate of accumulation of biomass in the water. So it's an essential parameter when it comes to a food chain. So the marine life depends on it, and eventually human activities and yes, and sustainability depends on such environmental parameter. So which is why it is very important to monitor it, and it is all the more important that primary production is expected to decrease in the next decades because of global warming. So which is what we'll be looking at that today and see what in the recent years are the trends over the North European shelf in net primary production, and how it can be correlated to other environmental parameters such as temperature, water pH, or nutrients in the water. So this is a quick presentation, so I won't execute every step in detail like I've done before, but to give you a quick look. So we'll use a little, here in this notebook, we will use a little more libraries than in the beginner one. We'll use SciPy, which is a collection which provides some statistics analysis functions, which will be very useful in this notebook. So I've quickly presented you in the beginner notebook the product that we're using here. So it's also the Atlantic European Northwest Shelf Ocean Biochemistry reanalysis. Here we will be looking at trends over 2 decades, so we'll only need the monthly mean values and not the daily values like before. So here is a little visualization of the extent of the data set. And of course, you want to know more, there is as well the quality information document and the product user manual about the product. But here we're not going to see the oxygen variable, but the net primary production variable in this data set. Same as before. So now you are quite familiar with the structure of the data set. So yes, same as we start with a basic plot of the net primary production. I see a single date here. It's June 2015. But what's interesting now is to see the trends in net primary production over the last 2 decades. So I've downloaded the data here from the year 2000 to the year 2000 to the end of 2019. So I have 20 years of we have 20 years of data. And what we want to look at is are there increasing or decreasing trends in the data, and in what regions are the most affected by those trends. So this is what I'm computing in this cell and plotting on this map on the period of 2000-2019. And we can see that, especially along the coast, net primary production tend to decrease over the last 20 years, especially in this area, which is called the German Bight. And next sections, there will be a focus on this area and see with other parameters what can be the possible correlations. So here is our area of interests. So I'm defining the extent of the box here, and I will subset all the next data sets to those latitudes and longitudes. So I've selected the data on these data sets. So now you are familiar with the cell function, but here with latitude and longitudes. And I'm averaging it spatially to have a time series of net primary concentration on this area. So here is what it looks like. In blue, I'm showing you the monthly values, and in green, those are the yearly values. So yearly means of the blue values. As we can see, it has a rather unexpected profile with a slight increase at the beginning of the century, but from about 2008, we can see that there is indeed a very noticeable decreasing in the data. And in the next sections, what we'll do is explore data sets of other variables to see if there are possible environmental drivers that could explain or be correlated to this decrease. So the variables we are looking at are pH, nutrients, so nitrate and phosphates, sea surface temperature, and salinity. As for the data sources, so those 3 variables come from the same data set as the net primary production data. So once again, the ocean biogeochemistry reanalysis. The SST are retrieved from satellite observation. So it's another product here. And the salinity is retrieved from an in-situ instrument located in the German Bight. So,
Alexandre, sorry to interrupt you. Could you please zoom on your window so that the text is bigger?
Oh, yes,
please.
Sure.
Great, thank you.
Is it better?
Yes.
Okay. Yeah, sorry about that. Perhaps this will make things easier also. Okay, so taking a first look at water pH. So I'm opening the dataset which stores the data pH. I've organized everything here. So same thing as with NPP, we have monthly values of pH in the water in the German Bight. So just as I did before, same manipulation, selecting the area of interest with lat min, lat max, longitude min, longitude max, performing the average spatially, resampling to have also yearly values, and now plotting the time series, which looks like this. So we can see that there is indeed a decrease in the pH in this area, but it's not quite the same profile as net primary production. So in the later section, we will calculate actually the correlations between all those series, but for now, visually, we can't really conclude. Same manipulation with nutrients, phosphates, nitrates, no familiar, latitude, maximum and minimum, yearly average, and plotting the 2 time series. So here we can see that we have profiles that are quite similar to what we have seen before with net primary production, which makes sense because primary production is often known to be very dependent on nutrient input. So we have strong candidates for environmental drivers of this decrease in NPP. Now let's look at temperature. So here, the data is a little bit different because now it's a different product, satellite observation of sea surface temperature. What's particular here is that the data set has a daily frequency. So over 20 years, it becomes very, too big in terms of memory. So it is actually split in 4 different files. So the first step is to merge them together to have only one full file, which will be easier to manipulate. So all those preprocessing steps are done here. And now let's see what is the evolution of temperature over the German bites. So with those cells, I'm just also splitting the temperature by seasons. So month 1, 2, and 3 are January, February, March. I'm considering those are the month of winter, and so on until October, November, and December. I'm plotting all those time series, and here's what I get. So here's just an illustration of the sea surface temperature, and those are the time series that I've computed. So here is taking into account the whole year, and those 4 are yearly values, but only considering one particular season for each plot. And as we can see, we can't really see a pattern that could be similar to the one we've seen with net primary production. And finally, manipulating in situ data again. Here is the fixed mooring that has taken the measurements that we are considering here. You can download it through the same portal as before. I think we can easily say it here. Is this one. So this data has a lot of variables. So just as I shown you in the beginner notebook, you have to make sure that the variable selecting is the salinity. So here is the seawater practical salinity, which we'll be considering. And here is the data which goes from 2000 to 2020, which is in our timeframe because we've selected this date range. As we can see, it's very noisy and it has a lot of missing values. So the first step is pre-processing the data to make sure we only keep values that are relevant to the analysis. And to do this, we will look at another variable in the dataset. So as I've shown you, we are considering practical salinity. But we are also considering this variable, which is actually a quality flag for the data. So each value corresponds to a value of salinity, and it comes with an integer from 0 to 9, which correspond to a quality evaluation. So for example, if this variable is equal to 1, it means that the corresponding point in salinity is good data. So you can see it better in this table. So I'll just actually clean this data by only selecting data that is good, probably good, or just interpolated and nominal. I'm excluding bad data, value chain, BO detection, missing values, etc. So yes, we can see that in the data that from the instrument, there are some bad data values here, change value here, and a lot of missing values as expected. And here is the data once it's clean, it still has missing values. So to have a better idea of the trend followed by salinity, I just averaged it by year. So here are the yearly values of salinity taken from this instrument. And now we have considered all the variables that we had chosen. We have seen visually what the profiles looks like. So now it's time to do some quantitative computing of the actual correlations between the time series and net primary production. So in this first example, I'm considering net primary production, its correlation with nitrates. So as a reminder, here are the two profiles that we had computed. So net primary production and nitrate in a yearly value of concentration. So I'm calculating the Pearson coefficient of correlation between the two profiles. And it gives me a correlation of 0.627. As a reminder, the closer a correlation is to 1, the stronger the correlation is. The stronger it is to -1, the stronger there is an inverse correlation, but the closer it is to 0, well, if it is very close to 0, there is likely no correlation. So here we have a quite strong correlation with a level of a p-value that is very low, which indicates a strong level of significance. So from this analysis, we can conclude that those two are well quite correlated. And we're doing the same manipulation for all the other parameters, so pH, nitrate, which we have just done, phosphates, SST, and salinity. It all ends up in this table. And so we can see that for the two nutrients, the correlations are very strong and the p-value is very low. So this indicates that, well, those two parameters are highly correlated to the net primary production, which again makes sense. pH has a solid correlation and a quite low p-value, but traditionally we consider statistical significance when the p-value is below 0.05. So this result is quite ambiguous, and perhaps we might get better correlations with pH in other areas. But as we can see with temperature and salinity, no solid correlation has been found in this area. So yeah, the potential drivers are probably nutrients in this area. So in this cell, this is a big cell to draw a conclusion plot about all the manipulation done in this notebook. So as a reminder, this was our area of interest, which showed very significant, a noticeable decreasing trend in net primary production. So this was our net primary production profile with monthly and yearly values. And here the profiles of nitrates and phosphates. And indeed, phosphates had a very similar profile as NPP, which is why the correlation was so strong, with an increase at the beginning of the century, and then a very noticeable decrease from 2008 2010. So yes, when you execute this notebook by yourself, you can do those little exercises. I think one of the most interesting is to explore other parts of the map. Here's an example of what you can get if you look at this area. So this is a profile of NPP that is constantly decreasing, and in this one, we found a higher correlation with pH than with the German bite. And of course, in this notebook, we have considered only a few variables, so temperature, salinity, nutrients, but there are plenty of parameters that you can also test by downloading other products. So don't hesitate to expand this analysis. It will help you master the data manipulation in CMEMS. So thank you for your attention, and I hope you enjoyed this lesson.
Thank you, Alexandre. It was a great presentation. Maybe we take some other questions, Andrea?
Yes, we sure can. And we have a lot of questions for you, Alexandre.
Oh, yeah.
Yes. So, first one. If I can see. Oh, yeah. How long is the pet? Okay, this one I can answer. How long is the Padlet available online? So there's no limit for the Padlet. It will be there. You can always access it. And besides the Padlet, you can also access our YouTube channel, Copernicus Marine Service, where you will have all the recordings of these sessions. But yeah, the Padlet will be available for you. No worries. Next one. Can you state, this one I think it's more for you, Alexandre. Can you state how to copy the directory from the shared to the Jupyter space?
Yes, what I advise you to do, perhaps I can quickly share my screen to
Sure.
To quickly show that. Okay. So what you can do is launch a terminal here. So you can see that it takes you to your home directory with the shared notebook here folder, which you want to copy the notebooks from. So you'll just have to run a copy command. So cp.r to retrieve the whole directory. So here is, for example, the notebook intermediate. So you have, so you just write the address of this folder, just like here, and copy it to your home directory. And well, it takes some time because it has to copy all the data sets that are quite big in memory, but in the end, they should appear then in your directory, and you will be able to open them.
And just to remind you that this information, they are all available on the participant manual that's available on the Padlet. So it's okay if you don't remember the line.
It's appearing here for me, but you can see the data. It takes some time to copy, but after a few minutes, it will be okay. Oh, yeah. Everything's here. Yeah, I hope it helps.
Yeah, I think so. Okay, I'll share again my screen to show you more questions. Next one. Are these training products also available in R? I think so far we haven't developed anything for R, right? Yeah.
No, but it's not the first time that the participant asks us for R codes, so we'll take this into account later, I think.
Yeah, maybe it is something to think about for the future. Okay, next one. If I wish to download sea surface temperature, salinity, pH, etc. for other area, can this download be possible with Copernicus website using this code without having in situ data? I don't know who would be the most appropriate. I don't know if you, Alexandre or Ergan, would you, which one of you would like to answer this question?
Well, if I understand correctly, yes, it is perfectly possible to download the products from the Copernicus website. Yes.
Okay. Next one. Would it be possible to use this code in Spider or a different program?
Well, yeah, it's as you want again.
I don't mind. Yes, it is possible. It may be easier to use it on a Jupyter Hub, whether it's the Copernicus one or your own Jupyter Hub. But again, on the participant manual and on the Padlet, you have plenty of information on how to install the environment, how to use the codes in your own computer. So yeah, you can do whatever you want with our exercises.
Great. Maybe we have some time for some more questions. Cool animation. Can we also save that as an MP4 or other video formats instead of GIF? Or would we then need to use a different command?
Alexandre, this one's for you.
Yes.
He's thinking, maybe.
I don't really know. I'm just familiar with the GIF saving method, so
yeah,
you'd have to read the documentation of the function to know that, perhaps.
We'll have a look and we'll tell you in the Q&A file.
Sure.
Yes, on that, just wanted to remind everyone that we will also answer all the questions that you have posted in Slido. So even if we don't answer them live, we will answer them and then post it on the Padlet. So you will have an answer. We can go to the next one. I had so much trouble using Cartopy, particularly installing dependencies like Geos, Shapely, and Pi SMP. I don't know how you read that, but did you experience that?
Well, personally, I
don't know. I've had no trouble importing the library, so
okay.
Yeah, it sounds strange, but
next one. Which one is easier to manipulate, OpenDAP or FTP files, and which one doesn't take more memory?
Well, the files that you download are the same with FTP or OpenDAP, so it all depends on the if you specify an area of interest or a specific date range to well only study what the period or the area that you are looking for. But the files you can design all take the same space if you request them the same way through FTP or OpenDAP.
Okay. And oh yeah, this question I think it's going to be for Martin. Can the codes be also applied to MATLAB? Thanks. Martin, you're still there?
Yep, I'm here.
Okay, great.
I think you can retrieve some articles in Copernicus Marine Hub Center to help you to use MATLAB or Julia. These languages are known by our team, and we have worked on several articles to help you to manipulate them. So maybe if you want to applied this training to MATLAB, it could be possible using our articles.
Great. Maybe we can try to post it maybe on the chat, the links to these articles, if that could be useful as well.
Yep.
Great. Do we have time for some more questions, maybe? How do you guys feel? Yes. Can you explain in more detail how you compute the trend for PP and what does the function NP polyfit years vals to 1 do, and what is vals 2 exactly?
Sure. So perhaps I'll just come back to the notebook to quickly show you
Yeah, I'll stop sharing.
How it works. Where am I? Okay. Share screen. So I think it was at the beginning of the notebook, if I remember correctly. Yes. So actually, as I'm showing here, here I'm storing the yearly value of net primary production. For convenience, actually, I'm just separating values and dates so they can fit in this function. So it's a function from MP that fits the data to a polynomial. And so one specifies that it's a polynomial of degree 1, so it's actually a linear regression. So that's what I hope it answers your question. And if I'm not clear, you can tell me.
Great. You can stop sharing your screen, Alexandre, so that guy. Yes, thanks. There you go. Oop. Some more questions. I think we were on, yes, not this one. Yes. Okay. I'm not sure if this is a good one, but my command delivers this that you can see. No module named Motu client. What have I done wrong?
I think you should install Motu client through a terminal with pip. I don't know if it's already explained the Padlet, perhaps.
Yes, we can also just add it to the Padlet, to the participant manual.
Yeah.
You mean,
well, basically, you basically just have to open a terminal in JupyterLab and execute a command pip install Motu client, and
we will.
I think then you'll be able to import Motu client.
Okay, we'll check if that information is in there. If not, we can add it. Great. So one last question. Any satellite or ground station data of nuclear leak, please? Maybe net primary production is lower due to nuclear leak to ocean or secret nuclear dump.
Probably. Well, if it's a secret nuclear dump, actually, I'm afraid I didn't have access to it, but
Yep.
That's probably, yeah. That's something to investigate for sure.
Okay. So I see we probably have more questions on Slido. We can always try to answer them at the end of this session. I suggest we take a little break now. 10 minutes, more or less. We can be back at 20 past 3. And we will have a presentation of Martin Pasquier, who's going to give a demonstration of the MyOcean viewer. So I hope you will be there. And I see you in 10 minutes.
Maybe, Andrea, you can share the slide of the coffee break.
Exactly. Everything has a delay. Yes. Yes. Okay. See you in 10 minutes. We are back. And now we're gonna have a presentation from Martin Pasquier, who's gonna give a little demonstration of my ocean viewer. I will stop sharing my screen. Martin, you can go whenever you want.
Thank you. Thank you, Andre. Greetings, everyone. I'm Martin, working at the user support team. Here today to introduce you to my ocean viewer and its main functionalities. It is accessible from our Copernicus Marine homepage by clicking on Ocean Visualization. We offer 3 types of visualization tools, my Ocean Learn for beginners, my Ocean Lite for intermediates, and my Ocean Pro for experts. I will show you for this presentation my Ocean Pro. I can reach it by clicking on this image or explore my Ocean Pro. Now you have access to the Ocean Pro visualization tool, and the default map is open. As you can see, 2 default layers are already displayed on the map: the seawater potential temperature and the mass concentration of chlorophyll A in seawater. We can start by clicking on Add Layer and access to the Copernicus Marine Data Store. Here are listed all the Copernicus Marine products. You can scroll to the right to see all of them, or clicking here. Here are listed the most popular products. Here the recently viewed ones, indicators and trends, news products in Copernicus Marine. And also you have the lists of each universe: the blue ocean, white ocean, and green ocean. On the left, you have filters to help you to discover our products. You can use keywords in this free text search bar, and you can add some parameters to your research, like time range, universe, main variables, area of interest, and so on. For this presentation, I want to focus on the Northwest Shelf region, and I will show you the salinity and temperature variable. Here I can select one of them and enter as a keyword the other one. With this selection, we have 4 products. Some of them are models and others observations, like in situ or satellite observations. Under each product, you have a short description of the product, how it was produced, if it's a model or observation. So also the geographical resolution, the temporal extents and the resolutions, and also the different variables you can display with this product. You can access to the glossary clicking on this information point. If you need more information about the product, you can click on the image and access to an overview of it. In this description page, you have the overview, what the product stands for and how it was produced, also the associated products and the DOI if you want to refer it in a paper, like these ones. Then you have all the information about the product, like its full name, the product ID, spatial resolution, temporal resolution, variables, and so on. If you spotted an error in these informations, you can send us a message through our chatbot directly clicking here. Then you also have access to notifications up to date, like general informations, incidents, improvements, and maintenances. You can click on one of them to access to all the details. In the Data Access tab, you have all the services available to open and download or visualize our data. Below each one of them, you have an information point to access to useful articles. Sorry. To understand how to use each of these services. Also, you have quick links to copy to your clipboard the dataset ID here and copy the URL to access to these services. At last, you have the possibility to download metadata by clicking on this download metadata button. As well, you can access to an article from our Help Center, clicking here. You can find the different ways to contact us in this section through our chatbot, through our online form, or via email. Then, in this description page, you also have the documentation about the license agreements, the scientific explanations, and technical contents. You can copy to clipboard the URL from this products page, clicking here. Then we will add to map the salinity and the temperature to be displayed on the map. You can click on Add to Map directly from the products page or over the image on Add to Map. Here you can see that there is 25 layers that can be displayed with this product. So I'm going to click here and access to all the dataset available. I'm going to add the salinity and the temperature layers, clicking on Add Layer. Then they are automatically displayed on the map, as you can see. Now I can move on the chart, zoom in by scrolling, zoom out by scrolling, and change the projection, which can be really useful for high and low latitude region. Now I can zoom in again, and I will show you all the functionalities available in this viewer. First, in the layers configuration window, you can remove some layers. I'm going to remove the default layers. I can also change the above layer priority like this. Here to see salinity above temperature. And I can also hide a layer, clicking on the hide. Here, and for each layer, you have the date displayed on the map and also the depth. The scale for the values, the subset and download button, which I will show you later. Here, you have the button to access to the products page. I just presented you before. You can also explore over layers from the same product. I'm going to change the seawater salinity and display the seawater velocity. I'm going to hide the seawater potential temperature to see it better, like this, yep. I can now configure my layer by clicking here, change its opacity, change the color map, like this. I can also change the minimum and maximum value. Let's take 0.3. I think will be updated on the map. Now I can mask out of range value by checking it. It will display, it will hide the values under the minimum and over the maximum value. In the case of some layers, like the seawater velocity, I can also show vectors to show the direction of velocity without or with a base map. Also, I can clear this value range, clicking here. and uncheck the mask out of range value. Last functionality here is to change the value scale to log. As you can see, the value scale is automatically updated. Let's see other functionalities. Here on the bottom, you have the time bar. The date displayed is the 26th of January 2023 at 12. I can zoom in by scrolling to increase the resolution and change the date as I want. Okay. Here on the right, you have the depth bar, which works as well. So I can zoom in again and change the depth. Now we can see the bathymetry. As you can see, below each layer, you have the information about the new date displayed and the new depth displayed. Now I can add some objects to my display, like points, lines, and areas. Graphics are automatically created for the variables of interest. I can add some graphics, clicking on Add Graph. I can also delete some graph or delete all these graphs. Let's delete this one. Last functionality with the graphs is that you can export samples to CSV or export graph to SVG. But first, like you can see, I have to log into my Copernicus Marine account first. If you don't already have one, you can register here. Also, if you have forgotten your password or username, you can click on these links. So I'm gonna log in. And now I can export a sample to CSV. It is important to know that even after you increase the resolution, it is always a sample and not the current data. Under the objects, you have the general settings. Here I can log out or log in. Also, I can register if I don't have any Copernicus Marine account. Then I can change the map settings. For example, increasing the resolution if I want to share an image with my colleague. I can change the projection. Here it's North Polar, as I displayed. I can also change the objects settings like units and so on. One of the most important functionality is the download and subset button. I need my Copernicus Marine account again, so I'm gonna log in. Here you can see that you can define an area on the map. I can change it afterwards as I want and delete them if I want to. I can clear this selection with this button. It is important to know that I can define the objects as the geographical area. For example, in the case of the area, it will download an area like the bounding box I'm just displaying right now. Then I can change the data range. Here you can see the valid data range I can display, I can download, sorry. So let's take, for example, 2019, and I want to download as the elevation range more levels of elevations. Here you can see that the subset is too large to be downloaded. It must not exceed the 1 GB limit. So I need to change my data range and elevation range. and or elevation range. So I'm going to change it again, like this. And now I can download my subset. Another way to download this subset is by clicking on Show API Request. Here you have the command line Vimo2 API Request you can use with our toolbox. Again, you have an article in our Help Center to help you to use it with this link. You can copy this command line by clicking here. It is copied to clipboard. If I want to hide these functionalities windows, I can press on my keyboard on Z here and show them again, pressing on Z again. Here on this button, information button, about, you have all the keyboard shortcuts that you could use with our visualization tool. Here you can share also your display with the current map, and also the objects and graphics. Clicking here, you can also create an image and download it with or without the chart legend. Download a video, customize it from the start date and stop date you want, set the step range. You can also create a GIF, change a video duration, move or let the chart legend as well, then generate and download your video. Lastly, you can copy and embed link from it. If you have any questions when you are using this viewer, you can send us a message directly through our chatbot, clicking here, and we will answer as fast as possible. It is also possible to check articles from our Help Center. For example, if I am interested in my Ocean Pro, I can see the article for the evolution of the different versions of my Ocean Pro. And in the case of this presentation, we have a dedicated article on how to visualize data with my Ocean Pro. There is a tutorial video and also a step-by-step guide you can follow. Thank you very much. It's the end of my presentation. If you have any questions or whatever, I will be glad to answer them. Thank you.
Thank you very much, Martin, for your presentation. We indeed have a few questions for you. Maybe Andrea will share her screen for to see the questions.
Yes. We sure have some questions for you. First one, My Ocean Pro, is this a free service?
Yes, of course. As I said, Copernicus Marine Services are free of charge, and creating Copernicus Marine account allows you to access to the full catalog. And so you have access to all the products I just show you in the in Copernicus Marine Store.
Next one. Can we also get code to generate the graphs videos directly from Python terminal, or is that only available to download data subsets?
Not sure to understand this question.
Mm-hmm.
I will read it again, sorry.
Oh. Oh no, it's here. Yes. It's right here.
Yes.
The one right on top.
It is possible to use the Motu REST request if you want to use the same subset within a Python environment. So I think it is compatible. I mean, you can subset in migration flow and use the Motu API request in your own Python environment to customize whatever you want or display as well within Python, your graphics and maps.
Okay, thank you. Another one, thanks Martin. How do I find out about the time for, say, the sea level velocity, given, for example, the Strait of Dover? The time seems crucial, or is it an average?
It's difficult to say. There's several temporal resolutions depending on the product you choose. So, I mean, there's some monthly products with one file that can be displayed per month. And in that case, it is an average for the month. It could be produced with monthly, with daily files or hourly files. Maybe it answers to your question.
Okay. The other ones, Ergan and Alexandra, so don't hesitate to jump in whenever you,
sure.
you feel like to complete any answer. And
Sure, yes.
thank you, Martin. And I think we have a few more. Let me check. Yes. Can the work be done to be exported as a map, legend, and title? If yes, can you show how a map can be created? How to export the work done in a JPEG or PDF format?
Yes, I will share again my screen.
Yeah, I'll stop sharing then. Go ahead.
And show it again. As I said, you can share and you can have an image from the current map you have with all the objects and graphics also. So, from here, on this chart legend, you have the value scales and the date. So you don't have any title, but you can customize it on an editor on your computer. I mean, it's okay. So you can download the image from the current map directly here. You have also the embed links here that you can copy.
Great. I'll share my screen again for a few more questions. So, yeah, this is good. This is good. Can we also get code to generate the graphs and videos directly from Python terminal, or is that available to download this data subsets? I'm not sure if this is for you, Martin. Do you think? Yes, still on the, yeah.
Yep.
So this one, Adrian. Can we also get code to generate the graphs and videos directly from Python terminal, or is that only available to download the data subsets?
You can generate the graphs as well within Python environment. I enjoin you to follow the different articles from our help center to help you to do so. And you can download the same dataset from there using the services of your choice. We also have articles dedicated to to other language than Python. You can access to OpenDAP, FTP, or Motu via using R, Julia, and MATLAB. Also.
Okay.
Thank
you. One more question. Can images downloaded from MyOcean Viewer be included in publications once the relevant product is referenced?
Yes, indeed. We have a dedicated article also in our web center to help you to know how to reference, how to make a good reference for Copernicus Marine data, and it works as well for MyOcean Viewer download or image sharing.
Great. So yeah, basically, there's a lot of information already on the website, Copernicus Marine Service. So you can just go there and find all these articles, as Martin said. Okay, and I think you've had enough questions for one session. I think we can pass on to our next speaker.
Thank you, everyone.
Thank you, Martin. I can maybe share my slide. Yes, there we go. I let you present.
Yes, sure. So
speaker,
we're now leaving the floor to Daria Andreevskaya from Noveltis as well, and she will present us the QGIS tutorials that we made for this workshop. Hi, Daria. You can share your screen.
Hi, everyone.
Hi, Daria.
So you hear me? I can begin?
Yes, we can hear you, yeah.
Yes.
You can share your screen.
Yeah, I can share my screen. Okay. So I hope you can see my screen.
Yes.
Yes.
Okay,
All
good. So hello, everyone. My name is Daria, as it was said, and I work at Noveltis. And today I'm here to show you how to use Copernicus Marine Service products, to work with them, to import them, and precisely in QGIS software, and also to use NetCDF to QGIS plugin, which is developed specifically for these purposes by Noveltis. So quickly, if someone is not familiar with QGIS, QGIS is a software application where GIS stands for Geographical Information System. So these type of applications, they are good to visualize and analyze different spatial and geographical data. And here we will use QGIS and a specific plugin, as I said. And this plugin, I'll say a bit more about it. So this plugin called NetCDF to GIS, and it was developed by Noveltis specifically to import conveniently NetCDF file formats. And this is very, very convenient in this regard that basically all products from Copernicus Marine Service, they are presented in this exact format. So to have this plugin, you can go to this website. You can here see the link, and I think it will be given to you in a dedicated platform. So you can see all the information on how to download this plugin, how to install it, of course, and how to use. So today, we are going to have two tutorials. One is dedicated for beginners audience, and then it will be the full tutorial, and then we'll have a little sneak peek of an advanced scenario, which if you want to see the full version, you can see the video, which is presented on the platform. And also there are both tutorials are presented PDF version in PDF tutorials. So if you want a step-by-step instruction on how to download data, how to download plugin, how to use it, and all the practical parts of QGIS, which we will see today, you can find everything in these PDF files. So moving to our first tutorial, it's for beginners, and both tutorials will be about Northwest European Shelf, a region of Atlantic Ocean, as it was said before. And just a quick reminder, these are shallow seas, shallow waters along the coast of European continent. And for beginners training, we will focus on the study of marine species habitats. And quickly, just a quick words is that to be a suitable habitat for marine species, this habitat should be coherent with several criteria, such as phytoplankton concentration, zooplankton concentration, oxygen, and so on. We're of course not going to look at all of them. And here we're going to use only two variables from Copernicus Marine Service products, which are phytoplankton concentration and oxygen concentration. Briefly, phytoplankton is basically food for all marine species, for which is the first level of the marine food chain. And oxygen, of course, if there's not enough oxygen in the water, then it endangers the marine species. So we will see on how these two variables, the evolution of these two variables in QGIS. And to have these products, to have these variables, you can have them. I think they're going to be provided to you on the platform, but you also can go and download them. And my colleagues already described you how you can do that. So these variables are both from ocean biogeochemistry reanalysis for this region. And you can see the temporal resolution, the temporal extent. And for our tutorial for today, we're going to use only, we are downloaded only monthly product for, let me remind, I think it's for, yes, it's monthly product from June 16th of 2021 to June 16th, 2022. So for 1 year. You of course are free to choose any other period and yeah, experiment with that. So what are we doing now? We're going back to our QGIS. So starting step by step, you need to, of course, open the QGIS software and create a new project. What else? So before I introduce you to the plugin, I'll first show how to add our map. So the map of the world for background for convenience. For this, we go to layer, add layer, and we choose add WMS layer. And here you need to choose map server demo, which is already loaded for me, but if you just start it, if you just opened the project, it might be not loaded. So for this, you need to click new, put name, whichever you want, and URL. URL for this specific layer is available on a PDF file for this tutorial. Since I already have it loaded, I just click on connect, I wait a bit, and I choose Blue Marble World. I click add and close. So now we have our beautiful map. We can zoom a bit to our region, and now we can start playing. So first what we do, first we add our netcdf files to the QGIS. And yeah, if someone doesn't know, netcdf file is a very convenient and common way of, if it's convenient format to store a lot of different variables, which could be nested and complex. So we open it, and here you can add it by clicking and browsing through your directories, but you can also do what I'm gonna do is quickly just choose the files you need and just drop them here. And I'll do this to see better. Okay, so we have two variables, which I already said. It's here it's dissolved oxygen concentration and a phytoplankton concentration. And first what we do is we're gonna briefly look at the dissolved oxygen. So basically, this tutorial is here for you to just to know how to use a basic features of QGIS if you are not familiar with this tool. So what we do, we choose our variable which we want to map, and we first choose dissolved oxygen, yes. So we choose it. Here you can see some information, you can see some metadata options about, you can play as you wish. And here we right click, and there are two functions, add layers or sequence layers. We will choose sequence layers, which difference is only in that when you add layers, they added directly to your project, and that's all. And sequence allows you to see animation of different time frames, for example, like here, to flash one after another. And here you see our dates and our actually depths, because the data which we downloaded has several depths, several levels. We're gonna use only one, for example, 3 meters. And we're gonna choose all our dates. You click first, Control Shift, click the last. Everything is good. Here, let's change the name to O2. And that's basically all. So you can click on Start, and you will see, let me move a bit, our animation playing. You can see here that our layers are changing. Oh, yes, QGIS is taking its time. And you can see that they're changing. It's really not visible because of the style of a layer, but we're gonna tune it now. So what we do is we stop our visualization because we don't need it anymore. We have our layers added. And now you can play with each of a layer. You can see that nothing really changes. So let's tune our layers. For this, we go to, for example, first one, right click, properties. And here you can tune as you wish. Basically, what we're gonna do is we're gonna put more neat numbers just for clear representation. We're going to put equal interval, and let's put up 5 classes. And here we can put only one label precision because we don't need more, as you can see here. You can also change, I don't know, your color ramp, for example. You can put it on rocket and make it from light to dark. You can invert it. So it will mean that lighter colors will represent smaller concentration, oxygen concentration, and darker color is, of course, higher concentration. So we did this, we click apply, okay. We see what our layer changed. The first layer, what was on top. So now we're gonna copy, right click, styles, copy style. And now we're gonna choose all our layers. You again, choose one, hold shift, choose all others, right click, paste style. So now all our layers are the same style, more representative. Now we really see that something is changing actually on the layers. And yes, now you know how to see the product, how to see specific variable in QGIS. So next, what we're going to do is we're going to choose only one specific data frame, time frame. For example, I'll choose March 16th. Which one? This one? Yeah. And yes, I will unclick all of them. So we have only this, for example, and we're gonna work with it. You can, of course, you're free to choose whatever time frame you want. So let's try to narrow down our study to a certain condition. So let's assume we want to know, for example, where concentration of oxygen is higher or lower than a specific value. So for this, what we want to do, we want to change the type of our layer. So it was raster layer, it is raster layer. Now what we want to do is to make it a vector layer. So for this, we need to polygonize it. We go to raster, conversion, polygonize. My window just popped in a different screen. So here, you choose your input layer. We chose 16th of March, whatever you chose. Name of a field, it's, what is it, was oxygen, right? And you can save it to temporary file here. So it will be only saved in your project. And when you close it, it will disappear. So you cannot restore it. Or you can save it to a file here to your directory to browse. You can browse and save to some place. It's up to you. I'm not going to save to not lose some time. So we click on run. We wait a bit. It might take some time. I hope it won't take too much time. But yeah, let's wait a bit. And after it will finish, we will do the so-called filtering. We will filter our data according to the condition. So for this, you can use any condition, yes, it's done. It's here, it's a bit ingested in the wrong place. Let's just move it up. Okay, so now you see our area, it was vectorized. And so now we want to filter it. So right click, filter. We have here fields on which you can filter. So we choose only our oxygen one. And let's put that it's, for example, more than 270. If I'm not mistaken, we have these values. Oopsie. Yes, I think so. But you can, of course, play. You put more or less the same amount and so on as you wish. It's up to you. You can test. And it says that it returned this amount of rows. And you can see that it's basically cropped our layer. We click OK. And now that's what we have. So basically in these areas, during this day, 16th of March, 2022, we have dissolved oxygen concentration higher than 270. If I'm not mistaken, it's millimole per cubic meter. So yeah, now we have that. And for example, next what we want to do, what we want to try is to see some specific part of our region. So this is our big northwest European shelf. Now, for example, we want to see only some part of its eastern part, for example, here. And we will learn how to create a user-defined polygon. So polygons are actually the type of a file is a shapefile. So we go to layer, create new layer, and we create new shapefile layer. You can here choose where you're gonna do it, and put your name. For example, what I put, I don't know, I put just new polygon. It doesn't really matter. New polygon. And you of course should choose the polygon geometry type because it's very important, because depending on the type of your layer, it will show you specific features, specific buttons that you can apply. So that's basically all. We put OK, and now we have a new layer which is empty because we did not create, oopsie, nothing. So right now we're going to create our polygon. So to do so, we first need to choose our layer and go to editing mode. We click on it. It's this pencil. And now we have, as you can see, some buttons they've been activated only after we click on the editing mode. So we need add polygon feature 1. We click on it. And now you can see this cursor, which allows you to put the extents of your new polygon. So again, you're free to play and you can do basically whatever shape you want. You just click, pam, pam, and for example, I don't know, here. And after you're done, after you put your the extent of your polygon, you just right click on it and this little window appears. You just put ID, doesn't really matter which one. Okay, so now we have this polygon, this basically just a geometry, nothing specific. And what we want to do is we actually want to have not this exact polygon, not this exact geometry, but we want to have this part, this purple layer, which we have before, but only in this region. So basically repeating this contour because we have our data only for ocean, of course, not for land. First, we need to close editing mode. You click on the pencil again. It asks if you want to save. Of course, you want to save. So we show our polygon. And now let's extract the vector layer, which we had corresponding to 16th of March dissolved oxygen concentration, and which is actually filtered. So on this polygon, on this new polygon. So we go to vector, geoprocessing tools, and should be intersection, I think. Yes, intersection. So we have this little window. So as an input layer, we can put yes, our new polygon, and overlay layer is our vectorized one, the only one we have. So what we also want to do, I think that's all. You again can save here or not saving, and I'm gonna run, and I'm more than sure that it's not gonna work. So we will see. Yes, it's not gonna work because as you see, it says to us that vectorized layer has invalid geometry. So yeah, this is very common, very common thing for conversion process between raster and vector layer. So what we're gonna do, we can easily, of course, fix it. So here on this layer, vectorized layer apparently has some invalid geometries. And to check this, you can literally go to processing toolbox and check it. To do so, you go and basically put check, and you have check validity function. By the way, if you don't have processing toolbox by any reason here, I think usually when you just open QGIS, it doesn't have it. You can go to, okay, my Zoom panel just covers half of my QGIS panel. Okay, so on QGIS panel, there's a processing, what is it? Tab, processing tab. And yeah, I don't see it because of Zoom, but you should see it if you have QGIS. You click on it, there's a first option, toolbox. You click on this toolbox and this beautiful, beautiful menu appears. So you go to check validity, and here you can check the validity of your geometries. For example, we want vectorized because it was said before that vectorized has invalid geometries, blah, blah, blah. So we put it, we run, and we close just to see. So, okay, I'll uncheck this in this because it's a bit, okay. So that these three layers were produced by check validity function, and you can see that yellow, this is a valid output. So all these polygons are valid. Good, great, that's what we want. And invalid output is red polygons. They somehow broken, something happened, I don't know. And we of course need to avoid that. So now you can choose them all and remove. We don't really need them. Yes, thank you. Let's put them back. And to fix our geometry, you choose your layer here, highlight it. You put fix in a search bar, and yes, there's fixed geometries. You put vectorized, again can save, run, close. Perfect. So now we have our fixed geometries. You can run check validity function again, and you will see that now there is no invalid output, there's only valid output. So that's what we need. So we go back to our extraction. It was extraction, if I'm not mistaken. And for this, we go back to vector geoprocessing tools intersection. Yes. So it didn't work first time because we had invalid geometries in our polygon. So now what we use, yes, as an input layer, we put fixed geometries, and overlay layer is our new polygon. Yes, run, take some time, close. Great. So now what you can see, we have these fixed geometries, which was dissolved, oxygen concentration filtered above 270 millimole per cubic meter, I believe. And yes, and this polygon we created for some specific area, which might be different for you. And here now what we can see is this the part of, so if you want to have only some part of a full, of a bigger vector layer, you can just intersect them, for example. There are of course many other options you can do with geoprocessing tools by difference and so on. What you can do now, for example, if you want a clear polygon without any basically data in it, because you can see that this polygon consists of many smaller polygons if you zoom in. And if you just need basically the shape of it with all the repeating of all the coast, you can go to Vector, Geoprocessing Tools, Dissolve. It has intersection by default, good, we run, and close. So now we have another layer created. And yes, you can see that all the polygons are now merged into one. It might be useful if you want, for example, to find an area under this under this threshold, under this polygon, which I am not going to show here, but it could be a nice exercise for you, or it's also, I think, in advanced exercise. So also here, it could be interesting, if you right click on a vector layer and go to open attribute table, oopsie doopsie, it's here, you can see the ID and you can see the basically which value of oxygen concentration this polygon has. We have several polygons. Yeah, we have it's for this one, yes. And if you want to know what is this ID, like what does it even mean, 9058, you just right click, put flash feature, and somewhere should flash. Probably we don't just see it. Yeah, okay, just very small and very close to the border, that's why we don't see it. Let me try again. Yes, so this one exact polygon has this value of oxygen concentration. And if we close it and we choose our dissolved one with only one polygon and open attribute table, we see only the, I think it's should be mean one, I'm not sure. But you see that you have only one because there was only one entity here. So that's basically it. It was the first exercise for this tutorial, for beginners tutorial. Now we will move to second part of it. So now we will work with phytoplankton concentration in seawater. And let me uncheck it. So now what we're going to do, we're going back to our netcdf plugin. So here, yeah, by the way, here you can see that you can add more netcdf files, but here in layers, you see all the layers you added by this plugin. This is not very important exactly here in this application, but in some applications, which is actually in advanced scenario, you might, you will need to use this tab. So we go back and I already put this file. So this is our phytoplankton. We go again, and now we're not gonna do the sequence layers as we did first time. We're gonna add layers. So you just see the difference, but yeah, usually you just add layers because you don't want to see the animation. So we again choose all of them, right? Yeah, phytoplankton, let's leave it. So we chose the same same time frame, same depth. We choose add and close. Yep, it's done. So now we have this. Okay, you can see again the difference, and we're gonna tune it a bit again because it might actually change the picture a lot. So let's briefly go to first one, right click properties, and yeah, you can see that we have very interesting color bar, which is not very representative. So equal interval, 5 classes only. 0, max, let's put 36. Yes, and you can see here what we don't need a big precision. 0 is okay. And let's play a bit and put a spectral palette from blue to red. So more rich with phytoplankton areas will be red or close to red, and with area with less phytoplankton concentration will be closer to blue. Apply, okay. So yeah, not much actually changed. So style, copy style, and let's spread it all over our timeframes. So yep, that's it. You can see the evolution of this variable. And what we're gonna do now is we're gonna learn how to, before we subset basically our own polygon, our own vector layer by creating it ourselves. What if we have some external layer and we want to have it and it's a vector layer? And what if we don't want to work with vector layers? As here, you can see there are vectors. Points and lines are also vector layers, by the way. And this is a raster layers with these little pixeled icons. What if we want to work with raster layer? So what we're going to do is we're going to use some other features of QGIS by applying another external layer to narrow down our analysis to a specific region. And this region we just chose to be Celtic Seas Echo region, which covers basically some here. And you can also create it yourself, of course, create your own new polygon. But here I'll show you how to add already existing layer. And this layer will be also provided with all other data. So what we do is we click on layer, add layer. So we don't create it now, we add one because it's already existent. We click add vector and we go and browse. So I have it in my data and I have this Celtic Seas folder. And we need a shapefile. You have several formats of the same file, and that's not for you, it's for QGIS. So you work basically almost all the time with shapefile, but when you create a shapefile, all these additional file formats of the same file, it creates automatically. So we open it, good, we add and close. So this beautiful and strange polygon has been added. So this is our Celtic Seas. And this, if you're interested where we took it, I created myself. That's easy. I could have created it just in front of you, but it was interesting to show you how to add external existing layers. So we have this one, it's a layer. This layer is again polygon. So what we're going to do now is we're gonna clip our raster layer. So this one, according to this new polygon with very strange shape. And yeah, let's again choose whatever raster layer. To be coherent, let's choose the same 16th of March, so this one. So we go to raster. I think it's extraction, yes, extraction, clip raster by mask layer. So it's already chosen, yes, when you highlight some layer in QGIS and then you click on some functions, features you want to do, it's automatically puts as input layer one what you highlighted before. But if it's not the case, just choose it among all the layers you have. So we choose this one. For mask layer, we choose our Celtic Seas. What we should add, is there something important? Yes, there's a very important thing. We need to tick a box, keep resolution of input raster. And also source CRS should be, I think, this one. Yeah, yeah, okay. It's the same as our coordinate reference system, CRS as coordinate reference system. It's given here in, what is it? It's right lower corner of your QGIS. So again, save, not save, run, close. So now we have our clipped mask. It's called. Let's drag it up. So that's how it looks like. Let's unclip our Celtic Sea and this. So now you can see a new raster layer created by clipping the previous one, the bigger one, clipped by the Celtic Seas region. And yes, it's a raster layer, so you can do the manipulations which are suitable for raster layers. But this one, again, is not very beautiful, just some black stuff. So let's just copy the style again and paste it. Where is it? Paste. Okay, beautiful. So basically that's it. If you want, you can of course clip any other layer, any other region, whatever. So yeah, so now you know how to subset your more precisely to some specific regions or polygons your data. So that was all for the second exercise, quite briefly. And so yeah, for this tutorial, it was all for this tutorial for beginners. We learned how to inject NetCDF files from Copernicus Marine Surveys product to the plugin, specific plugin into QGIS. We learned how to map them. We learned how to see animation, how to change styles, which can drastically change the output. We learned how to convert between raster and vector layers, which is very very common feature, common thing to do, common step. Also how to fix geometries to be able to perform our spatial analysis, because without fixed geometries, you simply cannot do that. And what else we learned to do? We learned to work a bit with external layers, how to import them, and also how to clip our raster according to some vector layer mask. So for the first exercise, that's all for the beginner's tutorial. And questions, I guess.
Thank you very much, Taya. That was a very, very clear presentation. I think we do have some questions indeed.
Yes, we do. If you could just stop sharing your
Yes.
screen.
Yes,
Thank you.
of course. Very easy.
Thank you for your presentation. Yep. It was really nice. I will now share my screen. So we can see Slido. If you, yes. Okay. It always takes a little bit longer. Okay, first question. Which is the last most stable QGIS version available? If we know that, just like
exactly.
We can quickly check it online and answer.
Yeah, I think yes. So that's my point. Also important to see is the version of which version of QGIS to use with a plugin. Because with some version it works perfectly. With some versions it can work a bit. It will work good, but to install it to your system, it will take some time and some pain, probably. But that's yeah.
Okay. Do you have like which version, for example, have you used here? Just so
here on my own computer, I used 3.20.3. And it was a bit, it was a struggle to install a plugin, but I also used another version. I believe it was 3.10 and it was easy peasy. So
it was okay. Okay. Next question. How to deal with NetCDF data that has longitude in the format 0 minus 360 rather than minus 180 minus 180?
Well, I think that from Copernicus Marine Surveys, all the data is in format minus 180, something like this. And what about this format? Well, I guess what you can do is to create a short and some little script in Python, for example, or any other language you are more comfortable with, to just transform your variables, your coordinates. I'm not sure you can do it in QGIS, but it might be, because in QGIS you have a different coordinate reference systems, so that might be also case for that.
Thank you. We have another one. What are the algorithms applied to obtain chlorophyll A biomass and phytoplankton diatoms plus phytoplankton concentration? Where can we have this information?
Okay, of course, I don't know how it will be obtained, because this data was not produced by me, but on the website, on the original, on the source of this product, you can see all the information, and I think there's some short description, also associated products. There's also, I think, some articles, some references. So you can just go to the links and to check all the data. And these links are also provided in a PDF version of tutorials. So it's detailed which exact variable, which exact product has been used during the tutorial.
Yeah, great. So all good with that. Yeah, we just did that one. Oh yeah. Are there any particular pros of QGIS over previous Python and MyOcean Pro Viewer applications, or is it just user preference choice?
Well, the main difference between these two is that in MyOcean Pro Viewer, you can view only the products of Marine Copernicus service. And in QGIS software, you can ingest basically any data you can find, any data you can create yourself. You can do a CSV, so Excel table, CSV format, TXT format, whichever you want, even yourself, and easily ingest it to QGIS by, of course, not using this plugin, NetCDF, because it's for NetCDF. But yes, you can use data from all over the places you can find in QGIS. And in MyOcean Pro Viewer, you can only use the available there datasets.
Okay. Thank you. We have another question over here. Can I get a brief information regarding the instruments used in the satellite and how they function?
I don't think that's a question for me. So
Yeah, no.
yes, I'm sorry, I cannot answer that question.
No, it's all right. I think Argan, you wanted to jump in on this
yes,
one.
I can share in the chat the link from the Copernicus service, which tells, which sums up all the satellites, all their instruments, and the variables they record.
Exactly. Perfect. Thank you. Yeah, exactly. Don't hesitate to also check the marine.copernicus.eu, where you will have all this information as well. Okay, thank you again. We can take maybe a few more questions before we, maybe one or two more questions, if that's all right with you.
Yeah, of course.
All right. So where are we?
It was down.
Yes.
Yeah, this one.
Yes,
the last one.
Exactly. This was preference. Information. I think we are.
Yes, there's the last one about ArcGIS.
Oh, I
already read it. Yep.
Oh yeah, where is that?
It's the last one down from Anonymous.
Yes, I can see it now. Sorry about that. Please can please can ArcGIS be used for the same purpose? If yes, kindly help out with how it can be used to achieve the same results. I use ArcGIS most of the time.
Okay, so me personally, I don't use ArcGIS, but yes, I heard about this, I read about it, and I think that QGIS community is very big, so you can find a lot of help in the internet for basically any application. About ArcGIS, I'm not sure, but I certainly saw a lot of questions about different features which are quite shared. And yes, a lot of users of exactly GIS applications, so geographical information systems, they use ArcGIS, and I believe it can be done, but how it can be done, that's not my field of knowledge. So yeah, sorry.
Mm-hmm. No, that's already very good. Okay, I think that was our last question. I guess you now will have a short demonstration of your advanced tutorial of QGIS. Great. Whenever you want, I'll start sharing my screen and we can carry on.
Yeah. Take. So you see my screen, I hope?
Yes, we do.
So now we move to a quick sneak peek of advanced tutorial, also in QGIS and the same region. And as I said before, if you want to have a full step-by-step instructions for this tutorial, you can find it on a platform, dedicated platform in PDF format and in full video format. So very briefly, what is it about? So again, the same region, Northwest European Shelf. And here we're gonna study river discharge. So river discharge is basically all the amount of water which all the rivers they bring to the ocean. And so it's a source of fresh water to the ocean, which is actually very important for marine processes. But as we all can guess, and I think we all know that besides fresh water, it also brings a lot of other stuff like different debris, vegetation debris, man-made debris, chemicals like phosphate, nitrates, and so on. And as some of the chemicals, actually some specific concentrations of some chemicals are actually beneficial for marine environment in specific regions, of course. But of course, an excessive amount of it can be damaging for marine species and for life itself. So here we're gonna exactly identify this river discharge, major river discharge in the Northwest European Shelf region of Atlantic Ocean, and estimate its impact on marine environment. So for this tutorial, we're being used 3 variables. Let me make it clear. Yes, 3 different variables. So one is taking, or actually 2, no, 1. Yeah, 1 is nitrite concentration, exactly the chemical, possible chemical pollution from rivers, which is also this product which you can see on your screen, I really hope. And it's also from ocean biogeochemistry reanalysis. Again, all the links you can find them in a PDF version of the tutorial. So yeah, here I think I already said it can be daily and monthly, and we are using daily products. So for this tutorial, we've been using only 2 months. It's April and May of 2020. It was chosen randomly. Again, you're free to choose whatever you want, play with periods and with dates. And the second and the third variables were taken from ocean physics reanalysis, and these 2 variables are seawater salinity and also the seawater velocity, so basically the current. And so moving to QGIS, where is it? It's here. So for this, it's as a sneak peek. I'm not gonna stop on each step, how to do what, like I did before. I'm just gonna show you basically the results of already existing project, which I developed before. So the tutorial is consisting of 3 parts, 3 exercises. And the first is very short, is to map and salinity of seawater and to see the to identify freshwater sources. So basically our river discharges. Here the salinity has been mapped, style has been changed. And here you can see I'll open the, yes, here you can see that the most salty places are this in blue, and the least salty are in red. So here you can see that ocean doesn't really change its salinity, and the least salty places are the ones that are next to the coast, and basically you can see that it's following the trend that it's exactly our river discharge places which we're interested in. On this representation, on this picture, we don't really see the rivers on the land, unfortunately. But if you open Google Maps, for example, you can clearly see and check what are these rivers. So what we did is we manually added points next to the least salty places. For example, here you can see to see actually the information. Oh no, I again don't see this panel. Okay, so you can actually see the information about the points. There's a little icon with a cursor and a little eye on a blue background, if I'm not mistaken. You can click on it. It should be somewhere here. I cannot access it because of Zoom panel. And then you click on basically any place where you have data, of course, and it will say you coordinates, it will give you coordinates and the value of, if it's a raster layer, it will give you also the value of this exact position. So you can see how salty water is here, for example, if you want to really like brief information about some point. So here we just put some points. For this, we added new layer, a new point layer, and manually placed it. You can add more, you can add less, you can add basically on each source of fresh water. I didn't do this because it takes time. So that was basically all for first exercise. It's not very long. It's just to see where are these major river discharges. And moving to second exercise. Let me untick. No, I'll untick only this. Yep. So second exercise, we mapped nitrate concentration. So to see the possible chemical pollution of a region from the rivers. And here you can see the results. So again, the darker colors, dark purple corresponds to bigger pollution, and the lighter colors correspond to less pollution. And yes, here you can clearly see that in the ocean, it seems, at least, we don't know the scale, right? But it seems okay, and you see how drastic change in the colors next to these rivers which we spotted. So here you can see how precise you spotted these river discharges. For example, here, yes, you don't really see it because it's on top. So let me put it somewhere here. Up. So yeah, here you can see, for example, that we spotted that here water was less salty, but very not very high nitrate concentration. And the opposite, for example, here we did not spot big change in salinity, but we can see a big nitrate concentration. So again, it also could be a nice exercise for you. It's also mentioned PDF file to maybe add more points, delete some other points, or change the position, because all these things you can do with point layers. So it's a nice lesson to know how to manipulate point layers. And for this here, it was for this tutorial, what we also did is we wanted to focus on one specific area, again, like in the previous exercise. So we created a polygon, just some random polygon. Again, you already know how to create it, so I don't need to explain it. And with this polygon, we also did what we already learned. We clipped an area. I'm gonna unclip it. So yeah, we clipped an area of one specific time frame of nitrate concentration. I don't remember which one was it, but yeah, it's one of these 5. It's not really that important. So we clipped this area, So now we have raster values which are corresponding only to specific region. What we also did is in this exercise is, let me move it back so to see it. We have these points, and what we did is we decided to extract the data about nitrate concentration on these points. So if you open the attribute table, you can see the ID of a point, you can see the concentration of it, the initial one. Don't look at the last one column. Let's pretend it's not existing yet. So this is what it gives you when you when you calculate raster values on specific points. To do this, you use a sample, I think. Yes, sample raster values function here in raster analysis, which is easy. You just input layer, which was our freshwater sources, raster layer, our whatever layer we chose. You run, close, bam, you have this new layer with points, and now with the data. So yes, and let me also, yes, I think if you flash feature, yes, you can see this point, for example. And yes, I think this one was, yeah, because when I flash feature, okay, so this one actually has a value of concentration, nitrate concentration, which is not supposed to have because it's not in our clipped area. But I guess it was, if I'm not mistaken, this was done on a whole raster area and not the clipped area. So you can do the clipped, and then out of 9 points, you will see that 3 values are missing because we don't belong to this area. So this column, now we see it, it's now existing. So you can see that this is also concentration, but in different units. So this one, by default, it's in millimole per cubic meter, I believe. Yes, it's here. You can see usually all the Copernicus Marine Service data, it has, for each variable, it has the units, which is very convenient. And we found an article in which it said that nitrate concentration higher than specific amount, exactly 10 milligrams per liter, can be can pose a danger for human beings, and even the lesser concentration can hurt already animals who live in this water. So we decided to check, is this concentration concentration is good? Is it lower than the specific this value, specific threshold? For this, we need to convert, and for this, we converted to milligrams per liter, and it's done by calculator field here. You can add new field with different type, precision. Here you can put basically whatever expression you want. Here are some little hints on which expression to use. And like this been added. There's a formula. Again, all the details you can find in PDF version of this tutorial. So here we can see that it's way less than 10 milligrams per liter, which means that this nitrate discharge in ocean does not pose any risk to humans and to animals. And also, so yeah, now we know this information, but we still want to know if it's, I mean, for example, here we can literally see that these nitrates were all gradually dissolved in water. So it means that they're not really spread it into the ocean. If you look at the full not clipped area, you see it's not big. And of course, somewhere it's going to be bigger concentration, somewhere smaller, because ocean is not stable, and so on. But yeah, also what we learned to do here is a next exercise. Let's leave it, I think. The last one, also very short, it's about the current seawater velocity. You can download from Copernicus Marine Service site, you can download the components eastward and northward, I believe, components of the current field. And they look like this. Let me show you. So like this, by themselves, they don't really show us anything because it's only one component of the same vector. So what we need to do is to vectorize it together in order to get our field, which is exactly this field. So here you can see, let me unclick it. You can see these arrows, which basically represent the direction of the current, and the color of arrow represent the velocity. So here you can see which velocities it goes. So like this, you can study how basically these nitrates are spreaded around the region, which are actually they're not spreaded because it's not that much. But you can of course use this knowledge, use these features for any other application, any other variable, and so on, any other product of Copernicus Marine Service. And yes, and maybe I'll very briefly show. So for example, that's what I said. Then you put here, when you add your new netcdf file and you add some layers, they all added layers, they go to this tab. And here, for example, this was done for previous tutorial for beginners, so it's not like coherent with what we see here. But in some, yeah, you can see here, for example, don't do this. It's not exactly the same, but you can see all the details again in a full video. For example, let's assume this is our 1 hour component. There are 2 components of our vector field, which we choose together by holding Control, right click, and there is this vectorize, which allows us to choose. You can see UV components, which is actually what we have here. You choose which one is east-west, which one is north-south. You choose if it's current or wind wave, which is current for us. You put output directory, file name, so on. And you choose a downsampling. So downsampling is basically how busy is your display. So for example, I think this exact field has been X5 downsampling. So it means that if it's X5, it means that right now you see 5 times less arrows where it was initially. So yeah, you see that if you would put X1 or no downsampling, none, yeah, instead of 1 arrow is going to be 5 more arrows, which can be too busy and can actually break a bit QGIS because it will take too much time to load everything. And that's basically all. Very little, very brief sneak peek into this. So yes, with this advanced tutorial, you can learn a bit. You can actually do the same stuff within beginners a bit to really remember how to do that without step-by-step instructions. You can, what you also can learn is how to manipulate points layers a bit, how to create fields, vector fields. It could be current, could be wind, wave, whatever. And what else we did? And yeah, like also how to add some more columns, more variables basically to attribute tables of vector layers using field calculator. And that was all. Hope it wasn't too fast. I hope you enjoyed it and learned something new, something useful.
Thank you very much, Daria. Yes, it was clear and yeah, great. And in case it was not, well, if it was too quick, just remind you that the videos will be available on the Padlet, and you'll be able to redo the exercise, taking your time.
I can stop.
Yes.
Exactly. Yeah, you can stop sharing your screen.
Okay, so before you all leave, we have several announcements to make, I think. So just to remind you that this workshop is not over. We will have a debriefing session on February 15th, where you will all be able to talk finally and to speak with our experts. So the experts from today's session and from yesterday's session, the experts that presented the products. So you'll be able to ask all your questions. We are going to send you a thank you email in which you will have all the links that we presented today, the links to the Padlet, to the material, etc. You will also, on the Padlet, find a Q&A section in which you will be able to ask all your questions. And you'll have also, finally, a feedback report. And we would really appreciate if you could tell us what you thought about this workshop. I think that's all for these little announcements.
I think that's all for this workshop indeed.
Yeah.
I hope you will be all present on the 15th of February for our debriefing session. And thank you everyone for being here, all the participants.
Yeah,
and
thank you
all of you to have shown all these interesting tutorials and demonstrations. Okay.
Yeah, thank you
Goodbye,
very
everyone.
much. See you on
Thank
February.
you. See you.